Right, so I want to go through this homework, with this paper. So it's also kind of like last week was kind of an old paper too. This is 2006, but anyway, so they're looking at they're looking at carbon and boron nitride, and they both have this feature that you have graphitic carbon, that's the lower energy state, and then you have diamond, which is a diamond cubic structure. And so that's it's like a face-centered cubic, like that, but it's not. If you go to the I think it's like one quarter position with that, and you put an atom there, and you have like an extra carbon in it. And that, so when you repeat that for every lattice position, so each of these would have a quarter transition. So it's FCC with this other atom. And it turns out that this boron nitride has that same thing, except I think that the boron and nitrogen swap for the carbons. So you have, I think it has like alternating BN in that diamond cubic structure. And strangely enough, it also forms like a graphite. So the graphitic structure is a hexagonal. So so conjugated means you go like single double bond. So this has a resonance structure. So it can go like that too. So this can flop there and just it resonates all the time. That means that these electrons are really stable. That's like a super stable sp3 bond, and it's planar. So the entire, when you have conjugated bonds, they're completely planar. So that means that this thing has to be, because there's another one here, so these will switch also with that one. So because they're conjugated and flipping all the time, they have to be in the same plane. Right. So the whole thing is this planar sheet, and then graphite forms these things like that. So if you think about the heat capacity, it's going to have this vibrations in the plane, but these are such strong bonds compared to the diamond. Diamond is just a covalent bond. So sp2. So basically these are weaker bonds than that, even though diamond is the strongest material. Right. So in plane, graphite has a super strength to it. Right. And then you get these kind of weird vibrations that are like wavy things like that, and then you have some kind of vibration like that, when the sheet's going to vibrate like that. So those are kind of low energy. There's a super high energy vibration, high frequency for that thing, and then there's a low frequency for these kind of weird things. Right? And diamond just has the one thing. It's just the bonds vibrating. Right. So these two are like a pair. The graphite and hexagonal boron nitride, and then the cubic boron nitride and diamond. They have similar. If you look at so these are the density of states. So if you throw energy into it, it's going to go into different frequencies, right? And the high frequency would be the strong bonds. H nu's energy. So the high energy is those are the in plane graphitic bonds vibrating. They're stronger than the diamond crystalline covalent bonds. And then you have these weak kind of wiggling of the sheet things, right? So and then the boron nitride has the same thing. It's got a weak part and it's got a really strong part for the in-plane vibrations, right? So that's kind of the theme of this. So as you think about temperature, so frequency, H nu's energy, and KT's energy too. So as you raise the temperature, you're kind of probing this density of states. You're filling these vibrations. In other words, it's as if he says in the thing, it's like you're filling a vase. That's his words in his paper. Somehow, it's not exactly this curve that you fill, but this density of states. So it's that density of states times times this weighting function, which is the Einstein heat capacity function, like this 1 over T squared an exponential thing. So it's like the Einstein heat capacity for like a free vibration from this past week's homework. So anyway, so that thing is really what he's talking about, filling the vase, and that's that he has like down here. So he's plotted the weighted phonon density of states. And then, so these would be the vases that he fills, kind of at different temperatures. They get excited differently because of this Bose-Einstein probability of finding that frequency. This 1/e⁻⁻1 probability is going to weight those so that they don't all fill. So that would be the temperature dependence of how it fills the density of states, which is this G nu thing. So anyways, that's kind of the theme of this. So strange. So the modulus, the heat capacity changes. If you go up to, in terms of these vibrational states, the heat capacity crosses. So you have like the diamond heat capacity has got a lower heat capacity than graphite. It's like you put diamond to your lip and it's cold. That's because of the low heat capacity. And I guess if you put graphite to your lip, it isn't cold. So you can tell the difference between diamond and graphite if you were blind and you didn't have fingers to touch it with by putting it on your lip. So because it's sheet-like, the reason why graphite's a soft material that can slide easily, like in that direction. So it's like a lubricant. So it's a soft material, and diamond's a hard material, like the hardest material, right? So there's a question of modulus of the material or tensile strength, and then the hardness, like two different things, right? So that the hardness is actually, you're going to go in and rip the stuff apart, like tear it into pieces. Like when so you're going to take some kind of either an indentation thing, so you have the surface, you're going to pound it with that, or you can scrape it. If you take diamond and scrape it on glass, the harder thing will scratch. So diamond will scratch glass, glass won't scratch diamond. Right? That's kind of how people test if it's just a fake diamond. And so anyway, so basically both the indentation test and the scratch test involve like ripping the thing apart, right? Versus the modulus. So the modulus, if you look at the modulus, so you plot like stress versus strain, and then you have the Hookean part. Right, and then that part means that you have the atoms, the crystal, and you're actually stretching a little bit. Right, so the Hookean part of that is basically the strength of the bonds that are holding this thing together. So that part is related to the heat capacity, right? So if you keep pulling this, something will happen. There's like a yield point. So there's a yield stress and yield strain. And then this thing will go down, and usually it'll go like that, and then you get another kind of Hookean part here, right? So this curve is really deceiving, right? Because if you don't look at the sample, you think that you'll think one thing. If you look at the sample, you'll think something completely different. Because the sample, when you go through this process, in this part, it goes from like that to maybe a little bit stretched. Like in a metal, this is like 0.5%, so 0.005 strain, right? So, and then in a polymer that could be like 2 or 3%, like quite a bit, polystyrene or something, right? So, okay, so once you get to here, it isn't that picture at all. This thing becomes like this. So you have part of it that's not deformed or is Hookean, deformed Hookean, right? And you're going to have like a neck forming of some kind, and it's going to look like that. Then all the action is at this kind of yield point, the yield zone. Right? So you have two yield zones that form there. So this part's Hookean, that part's Hookean, and all the action is in this kind of infinitesimally small region in a metal that's like disclinations. And in polymers, that's shear bands, can be shear bands in metals too, or it can be crazy in polymers. So some kind of, these are all like localized mechanisms or something. And this is all bulk, but that's a bulk mechanism. So you're going in this yielding process, you're going from bulk to localized. It's a different phenomenon that's going on. So the curve is completely misleading, right? Like it's nothing like what you think. It's not the material properties. You change from a localized from a global to a localized phenomenon. And then what happens in this is the yield zone. So in the yield zone, the yield zones eat up the material. So they eat up, so it'll get to the point where it's just all stretched out, and then it's like that. And at that point, you can't do it anymore. It's all this stuff, and this stuff it behaves Hookean. So it goes up, and then it finally fails. Right. So looking at that curve, it's kind of misleading. Anyway, this part would be related to this heat capacity, and the slope of this thing is that's the modulus, like the stress over the strain, the Hookean strain, Hookean everything, HHH. And then you have the yield point, and here's the plastic behavior. That'll be more like the hardness. Right. So anyway, there's two different. The reason I mentioned that is that he says right at the beginning, like this stuff is the hardest thing on Earth. Like it can't possibly be that the graphite could be better because the graphite is one of the softest things on Earth. And then he says like that's not right because soft and hard doesn't have anything to do with like the modulus. They're separate things. Like how easy it is to rip it apart. So graphite's easy to rip apart because it's sheets, so they just slide. And diamond isn't because it's tough. It's all glued together in a 3D crystal, right? So anyway, so that's one thing. And here is like kind of interesting that he brings that up. Anyway, and then he says like the different vibrations that you can get, the acoustic and the optical vibrations that I talked about in class. And then he wants to get the Dubai temperature for this. So he's going to do a computer simulation because what he wants to see is where there's a transition at 1,000 degrees C where the heat capacity of diamond gets higher than the heat capacity of graphite, and with a lower heat capacity, you have a higher modulus. So above 1,000 degrees, graphite is harder. It's not harder. Graphite has a higher modulus than diamond, which is an odd thing. And so does this boron nitrate has the same phenomena. They swap at 1,000. This is like at 600 degrees Kelvin. So the two have the same behavior, and he's saying basically that. So, and if you look at this is showing the difference in the heat capacity between the graphitic and the diamond. So it goes up, and then finally it drops down and drops below zero, meaning that the graphite's got a higher heat capacity than the diamond, right? And then he also figures out the Dubai temperatures for that, and it shows the same behavior because it's related. He gets the Dubai from the heat capacity and from the model and everything. So anyway, he comes to the conclusion that it's because he's exciting this high order. When you raise the temperature, H nu's energy, KT's energy. So this is like temperature down here. So as you heat it more, you excite more of these high frequency vibrations, and then you find out that there's this big peak for the in-plane graphite sheets that isn't there for the diamond, and that only activates at a high temperature. And for carbon, it's 1,000 degrees, and for boron nitride, it's 600 to light off the in-plane vibrations of graphite. So to do that, so he goes through the whole routine with this. So he's got the Einstein equation, he's got the Dubai equation. So he does a density functional theory simulation of it. So he uses this vast sort of Vienna ab initio simulation. Ab initio means you're starting from an electron, like you're starting from basic molecular atomic units, subatomic particles. Then you're gonna figure out the electron cloud. You're gonna build the crystal. So he's gonna choose the elements, and he's gonna treat the electrons quantum mechanically using density
functional theory. They say that right? I think I said it right. So anyway, that's basically like doing a quantum mechanical wave calculation for the electrons, but it involves a series of cheats because you can't do quantum mechanical calculations on real things. So you have to cheat to do it. And there's several ways to cheat, which are called approximations, right? So the cheats that he does, like he says what he does here, Hartree-Fock approximation. That means he's cheating. He isn't really doing the calculation. He's inventing the answer kind of, but it kind of works. So these are, and he uses this COM-SHAM equation. So he kind of plugs in some kind of cheats to get it, so he can get the electron structure or something like it. Then he has the atom, and then he does like two things to it. I mean, within this vast program, which he just bought, so he just sort of plug and play kind of thing. And the program's going to either do molecular dynamic simulation to relax the thing. So you have the thing, you set it up with the density functional. So you have all the electron clouds are all associated together. You put it into the crystal, and to take that crystal and let it just follow Newton's laws, like move. There's forces between them because they have charges or the repulsive interactions, like Lennard-Jones potential. Just let those go and like move the particles around and let it shake and bake until either the density reaches a constant number that's a reasonable number, or the energy reaches a number that's a reasonable number. So you're gonna wait, cycle. It'll start out beginning, it'll have like you plot the energy, it'll be a high value, and it should like come down and reach some plateau. And the same with the density. So the density might have a higher or low number, and it might oscillate. So it might not be so straightforward. At some point you say, I'm done. Right. Then you say that's the structure that I have. And then he's got another. You can also minimize the forces, obtain a stable structure. So there's two ways that he does it. The first one's kind of like the Monte Carlo thing, and the second basically is molecular dynamic simulation. So the VASP includes all that. You put your stuff in and it does it, basically. But I think the VASP is going to cost you like 200 grand. It's not cheap. Right? These density functional programs, they're black boxes, and it's expensive. They aren't cheap. So anyway, so you write a grant to try to get that if you want to do that kind of work. Or you find someone that has it and take it from them, or whatever. But anyway, so what else is going on here? So he does that. So that's how he gets the crystal. Then from that, once he has the crystal, he can get the from that simulation. If he did the molecular dynamics, he can get the vibrational density of states from the crystal. And once he has the density of states, he can integrate it with this weird thing. Okay, so he integrates that. He can get the free energy, take the derivative of free energy, and get the heat capacity. Right, so he runs this program, gets the density, gets the structure, gets the density of states, then integrates that and gets the energy, vibrational energy for the structure, and then he's going to take the derivative of that to get the heat capacity. So this is the Helmholtz free energies. You have so you can call this F like that. So you have the Helmholtz free energy. So his is F is U. So it's U minus ST, right? And then you know that in this BF is minus PdV, and then TdS or minus SdT. Right. So if you want to know BF dt gives you minus S at constant V, which we're looking for CV, so it's a constant V. And if you have you want to get U, right? So U equals F plus TS. But minus S is F dt, so it's F minus T dF dt, constant T. You want kind of want U D because you're going to do du dt at constant V is Cp. There. So that's how it's. So if you get F, then you can get U. If you get U, you can get the U dt, which is Cv. And so
So we have the CP minus CV equals, there's an alpha squared over kappa P, and there's another P, right? So if you're at, like, say you're at absolute zero, then delta CP is zero. So if you're looking at low temperature, then you get this difference between CP and CV only comes to play when you're at height, like at 1,000 Kelvin, then that would come into play, but if you're at zero, it doesn't matter. And you'll see, like, in his plots, that's true too. And that's for an ideal gas, right? But basically that's kind of a rule of thumb. So he's got the delta CP. So when he gets to low temperature, it goes to zero. This is the difference between the two. That's right, it is a difference. So basically you're looking for this thing to go to zero at absolute zero. This is between diamond and graphite. The difference, the CP, I thought he had that plot here. CP minus CV or something. I thought he'd have that in here, but actually it's not here, it's in something else. But anyway, it'll go to zero. The two curves will be on top of each other. Let's see, doesn't he have a plot of CP? Yeah, this is CP and CV. Okay, so the black curve on the dashed one, I think, is CV. You can't see the dashed one because they're right on top of each other until you get to, like, out here. I think you can start to see the dash in the straight line separate, maybe not. So you can see the dashed here. So somehow they separate in here, like the black dash follows the red curve. That's why it's underneath the red curve for that one. So at high temperature, they separate. Here you can see the black line and the dashed black line is, I think CV is the lower one. CP is the upper one. So at the low end, when you're at the low temperature, they're just the same. And then only when you get to 700 for this one and kind of 1,000 something for this one do they deviate, right? So anyway, so that's another thing in this paper that you could get out of it. All right, let me just go back. So that's kind of the routine. So he's getting F, but he can get CV because he's going to convert. He's going to use F minus dF dt times T to get U, and take a derivative of that and then get CV from that. Right, and then, all right, then once he does that, then he has, like, the Debye equation for CV. If he knows the density of states, so this W thing is, the weighting thing is that, and then CV is the integral of that times that. Anyway, so he can fit that to this Debye equation. He can get the density of states and he can calculate CV directly, or he can get it from this energy. Well, this also includes the density of states. So density of states gives you a CV. That's what he gets that from his simulation. Then he has a Debye equation. He fits the CV that he got to that with the one parameter. The one fitting parameter here is the theta D, Debye temperature. So that's how he gets the Debye temperature. Right. He's gonna make a simulation, make his molecule, let molecular dynamics relax it down. Then from the molecular dynamics, look at the vibrations that he has from it, which gives him the density of states because they each have a different energy. He knows how many. You can add them up. Then you get the number versus the frequency. That's the G of nu. Then he's going to use this equation to get F. So where did this equation come from? That equation is in the notes. I posted it under the homework, so you don't have to search for it. But anyway, so you got, we have this expression for the partition function for the sum of states. So this is the normalization factor, and log of the normalization factor gives you the free energy, the Helmholtz free energy. Beta is KT. So you have 1 over KT on this thing. So if you put that in, so this guy isn't in the form ln of exponential. So if you take exponential of this, and then take log of it, that gives you this. So you can, and log of something plus something is log of the thing times that thing. So this, if you work that out that way, and you have to put a beta into this too to make this work. But anyway, if you work that out, you'll get like this expression, which happens to be already defined as a function called the sinc function, which is something you probably have. It's a hyperbolic sine function. It's something you've probably never seen and never will see again,
So it's like hyperbolic sine, hyperbolic cosine, hyperbolic tangent. And they look like this. They don't look anything like sine or tangent. The tangent looks like this tangent, the tan H function could be a pretty useful function because it's a switch function. It's like on off, -1, +1. So if you have some kind of scenario where you see a thing goes on off and it's got a breadth of the action that happens, then you could use the tank function to fit that if you wanted. I'm not sure what the meaning of that would be, except that the tank function you can convert back into exponentials, and exponential is useful because it's always like energy over kT, so you could work it back to some energy. Like there would be an energy of the switch from that, I guess, if you wanted to go down that road. Not many people have gone down that road. Okay, yet this is probably the only case where you'll see routinely that they're just so free energy from this expression, which is a little bulky, can be compressed into this one function, even though this function nobody really knows what it is. I mean, offhand, you can figure it out, but basically it's not something you're familiar with. It's not like a sine function. So anyway, so if you want to confuse people, you'll use this form. That's kind of what he here. So that's what he has here, sync H whatever. That's our X or energy thing from the bi. Right, so that's just the partition function. So he's normalizing with the partition function. That's the normal way to do this. So that's the same function as what we've had. It's just written in this compressed form to make it confusing. So, I mean, probably if you do this kind of thing all the time, this would become like a handy way to do things. It cuts down the number of terms you're writing to 1 instead of 4 or 5. That's handy. So there's that business. And then fitting the curve. All right, so then he wants to get from this, he wants to get the modulus. Okay, so we had that. Oh, let's try open this thing. So one reason why. So 27, I think. Let's see. Not update now. Enable. I don't know why it always has enable, but so 27. Oops, 27. Is that the right thing? 28. Oops, 27. So if you have like so you do a force balance, you have mass times acceleration is a spring constant. If you have just so it's called a harmonic approximation if you use the spring. And he keeps saying like in this paper, he always says harmonic, meaning that the springs between the atoms, which is kind of the basis of all the Einstein and Debye, even though Einstein has kind of a guitar string for the spring, and Debye has this whatever else, a multiple frequency thing, the sine curve for the dispersion function. So anyway, they call all those things are included in the harmonic assumption. So which makes you wonder what's the anharmonic, which you'll see. So the anharmonic, so in the harmonic assumption, there's no thermal expansion. So, and there's also no non-spring-like vibrations that go on. So everything else is called anharmonic. Thermal expansion is the main thing. So there's always like an anharmonic component to the heat capacity, which is a small number compared to the harmonic. Like if there's a difference between the Debye function and the heat capacity, you say those are anharmonic vibrations, which is a catch-all to saying like you don't know what it is, but it could be thermal expansion. And so anyway, so this is a harmonic approximation. It's a harmonic oscillator. You say that the mass times acceleration equals spring constant times x, and then you plug in the what do? You plug in this x. Would be like a sine function for the. So you just solve that and you'll get the square root of k for the frequency. You plug into this a sine function, the frequency times time, and then you solve it, and you find out that you'll find out that the frequency is the square root of the spring constant divided by mass, and if it's a bulk material, the spring constant is related to the bulk modulus. It's kind of the square root of the Debye frequency would give you the modulus. That's the idea, and it comes just so that's called a harmonic approximation. So so he does that, but he does it with this Birch-Mergahan equation of state, which is you can Google that, so it's linked in there, but basically it's this thing, it's like PV and RT type thing. But if you take P times V, you get energy, so you can calculate the energy in terms of the modulus, V0. And the derivative of the modulus with respect to the volume, I guess. And then, anyway, that's his Birch Murdahan, Murnaghan. That's a hard word to pronounce, but anyway, that's the equation of state. From this, you just get the modulus from it. So there's all right, so that isn't what so in this case, you have to calculate the modulus, so that's not going to help you, right? It asks you to take the Debye temperature in the homework and calculate the modulus from it. So he gives it Debye temperature somewhere here. There was a table of the Debye temperatures, but anyway, he gives the values somewhere in here for the Debye temperatures for these things. The homework asks you to do something like that. Calculate the Debye stiffness for diamond and graphite as mentioned by Tohei. Oh, it's another paper. So Tohei, so he cites Tohei to say how he got the modulus. And Tohei is this, I think it's this paper. No. That's Tohei. Oh, Tohei, right, he does it, but he cites this paper, which isn't Tohei. Tohei's a parent paper, but this is the thing where they tell, and it's 2001, so it's kind of old, but and then they give an equation for it at the end. I think it's the last equation, the way I remember it. Then what would be, I thought it was like absolutely the last equation in this. Here, yeah. So there's a bulk modulus. M is the molecular weight. R0, don't remember what R0 is. That's Planck's constant, and then KB is a Boltzmann constant. So that guy can give you the bulk modulus if you figure out what R0 is. I don't remember what R0 is. It might be the atomic spacing or something like that. Here's R0. The Wigner-Steitz radius, R0. So I think you can just use the atomic radius from that. Let's see what that is exactly. You need that. Parameter normally reported in atomic units. It's useful. 3D system and free defined by V by N. Does he say, oh, valence electrons in a volume V. 3D system, N free valence electrons in a volume V. S. 3 over 4 pi N. Oh, here, they give the value versus A0 is, I think, the atomic spacing in the crystal. So RS, unfortunately, doesn't give it for carbon. Oh, here, Wigner-Steitz radius are related to electron density by the formula. Okay, so if you know the electron density, so if you know the mass density and the number of electrons, you can get the electron density, then you get the Wigner-Steitz radius. I guess maybe you're going to need to do that. Like just find the mass density of carbon, of diamond and graphite. And then the number of electrons, electron density, the mass, so per mass, so you have like electrons for carbon is like 12 electrons per 12 grams per mole times Na things per mole, or divided by Na things per mole will give you like the electron density. I think they'll give you the number of electrons. They'll give you electrons per gram, and then you have the mass density, which is grams per centimeter cubed. So if you multiply that by this thing, that'll give you the electron density, whatever this thing is. This is the number of electrons per gram. So if you do that, then you get this number, and then that number goes into this equation, and you get the RS, this Wigner widths, Works, whatever it is. Wigner Stites radius. You can plug into the guy's last equation in that paper here. And if you have the Wigner Stites radius, where's his last equation? You can plug it in here, and then you know the molecular weight. You can find Planck's constant and the Boltzmann constant, some weird numbers. And if you have the divide temperature, you can get the modulus. And then the modulus should come out right within like 10% of whatever number you find. Like you can find the modulus of diamonds somewhere. So maybe there's one thing that gets all those numbers. Young's modulus is 12,000 gigapascal, Schur modulus, Young's modulus, graphite 1.796, 11.5 gigapascal. So it's 1200 versus 11.5. Your numbers should come out like some 1,000 times different, or 100 times different. Too. So it asks you to do that. Let's see what else is here. No, he does that. He does that and gets the modulus too in here. So it's got this paper. It kind of has everything in it, you know, and it's kind of got a little story, so it's nice, I guess. All right, I always forget about what he uses these acronyms. So LDA. So you have to go back and find where he first mentions it. It is like all listed here. LD, when you find it out and it's like something, oh yeah, obviously it's that, but like quasi-harmonic approximation uses spring. So QHA or sometimes HA, he'll just use those symbols and you have to figure out what it is. What is that? What did it say? LDA. It's local density approximation. Correlation effect retreated by the local density approximation. This is just how he did the simulation. So you have to have anyway, there's different approximation. You don't need to know what they are, I don't think. I mean, you can look it up if you want, but basically LDA is a local density approximation. And then so like here's a harmonic approximation. So he keeps using the symbols, like you have to kind of go back and figure out what he says. So he gets both the divide temperature changes, switches, the heat capacity switches, and at 1,000 degrees C for the two. And he's got a plot with all the different vibrations in the crystal. So you can say, so the way he plots it, this is density of states. You can see which vibrations contribute to which of the peaks. Right. So he's got, I think they're labeled here, right? Photon dispersion relations for the solid curves show the calculated dispersions. The Boolean zone have been obtained by measuring different scattering with experimental values. He mentions in the text what each of these are, but these are the optical, like in other words, the ones that go to zero at zero, those are the acoustic vibrations of the various bonds, and these are the optical vibrations, right? So the optical vibrations in plane of the graph of these are the optical vibrations within so the covalent bond stretching of the diamond give rise to the giant peak. And then the optical vibrations within the plane of the sheet of the graphite give rise to the peaks at the high temperature, high frequency for graphite. And the same with this hexagonal boron nitride. So you can tie like which which vibration gives rise to which of the peaks in the density of states. And the density of states, what you're going to use to get the heat capacity and the modulus and the Debye temperature, right, through that integral. So anyway, I think that's pretty much what he's going through here. What else is here? VASP, the sink, that thing. Hopefully this will work out. And then what's the difference between optical and acoustic phonons? So we talked about that. So basically, the only thing I've seen about it is that you have NaCl. So materials that aren't crystals like NaCl, like diamond, also have optical phonons. So I think in that case, NaCl, if you remember, so if you put an electric field, like, so you're gonna have electric field from a wave. And then you're gonna have your crystals, you have like Na plus, Cl minus, Na plus, and then this is a 100 plane. So if this wave comes in, then this guy goes up or down, and this guy goes down or up. And so they're going in opposite directions. If it's a normal transverse wave, then they would all follow like a wave. They'd all go up at the same time. Right? They'd follow a wave through the crystal. There's also a wave of this, but the things are moving in opposite directions. Right? So this is optical, this is acoustic. And that's for a transverse wave. For a longitudinal wave, they would like compress, but the chlorine would expand while the sodium compressed, if you can imagine that. So you have a crystal with two atoms in it, and one of them is compressing, the other one is expanding at the same time. It's almost like a shear thing going on. It's like a shear with the crystal planes or atoms or whatever. So you can see how that could work with an electric field with sodium chloride. But if you have carbon, so you just have diamond, like how can that happen? It doesn't happen. Like it doesn't happen with light. So diamonds like that, and there's this other 1/4 transition. There's another FCC if you look at the 100. So anyway, so despite that you can't imagine how it could happen, it's possible that the atoms can vibrate that way. So if you dump energy into it, they can do a wave kind of thing, or they can do this other vibration. It's less likely to do the other vibration, but it's possible. So it's like a higher energy vibration, the optical. So that's why in this plot, it's just harder to do. So it's a higher energy vibration. So you'd have to go to high temperature. So here, see, this is a higher frequency H news energy. So it's a higher energy vibration for the optical, and it shows up the high end. And the acoustic is a lower energy. Right. So even lower energy, these like electron transitions, a lot of magnetic transitions. So there's a lot of vibrations, quote unquote vibrations, right? So different things can happen at low energy that don't happen at high energy. So optical is the highest energy stuff because it's this weird, so you can't even imagine how it could happen, but somehow that vibration is possible on that crystal. And if it's possible, it will happen if you reach the right temperature. So it's hard for it to do, but it's going to take a high frequency to reach that. So you can think about if you put it in a sonicator machine or something and crank it up as high as you can get it, then every vibration is going to happen. The things that wouldn't happen if you just hit it with a hammer are going to happen if you put it under such high energy. So that's kind of the idea that the way this works. So anyway, so even in carbon, just pure carbon, there's optical and acoustic vibrations that are going on, and they just happen with different energies. So that usually the model for it is NaCl, that same vibration can happen because it's easy to visualize how it could happen in a crystal, like an ionic crystal. So stiffness, so they're both, neither is, all right, so both related to stiffness. They both contribute to stiffness. And they both contribute to heat capacity because they're eating up energy. But neither is related to hardness because hardness involves not vibrating the crystal, but ripping the thing apart. Right, so that's like the bond strength. It It doesn't have to do with vibrations. That's why he brings it up at the beginning of the paper. He talks about diamond, and it's like, well, what do you know about diamond? It's the hardest thing in the world. So, and then graphite, and he says like the transition at 1,000 degrees C, it doesn't make any sense. But he starts off by saying it doesn't have to do with hardness. It has to do with this strength. And then is the heat capacity related to hardness? No. And then he states that very frequently proportional to the square root of the stiffness, then the harmonic approximation derive that. So that's basically this mass times acceleration equals force times a spring constant, and then put in a sine wave for it and then solve it. You'll find out that the frequency is proportional to the square root of the spring constant divided by the mass, or equal to that, I think. So basically that gives you the relationship on it of a spring constant between atoms, which is the basis for the modulus. And then that other paper gives the more detailed, like the dirty part of how to get that. And it still is like square root of modulus by mass, but basically it's got a lot of other terms in it because he's going to 3D. He's taken that and he's taken it from a spring, from a harmonic spring to like an actual atom. So it's got Planck's constant in it, Planck's, Boltzmann, whatever. So it's going like from atomic to molar, and then you get this Debye temperature, whatever this stuff. If you really want to know what all that stuff is, it's a constant. And then that constant comes from this whole paper, which is, I don't know, 7, 8 pages long of equations that are marginally understandable. You can read it if you want. I haven't really bothered to read it, but I think the last equation is all you need. Anyway, so it's that business. And then calculated by stiffness, that's using that equation. Use the Debye temperatures he gives, and then calculate the stiffness, and then compare it with whatever you can get from Google for the modulus of diamond and of graphite and of maybe the carbon nitride thing. Then this guy, it's interesting he mentions this guy Wunderlich, because he's a polymer guy. Wunderlich's the guy who does the heat capacity for polymers at the end of the notes, so I'll go through. So the same guy is talking about projected. So the reason that he made this paper is because Wunderlich had said that the heat capacity of graphite becomes smaller than the diamond at above 1,000 K. So Wunderlich measured it. Apparently the heat capacity measurements at such high temperature are almost impossible to do. So the error bar is huge. So he mentioned this in the beginning of the paper. So he says like the way to do it is to do this density functional theory simulation and figure out if it's really true. And he gets a number, he shows the numbers that he gets are almost exactly the same as the experimental or whatever. Like the dots are experimental values for heat capacity. So he's matched it up with his density functional. It's pretty close. So it's better than what you'd expect. And then derive his equation 3. So equation 3 is a Debye equation, which you can get, it's in the notes, how to derive it. I mean, I did it, right? So, it's like 57 or something here, I think, or either 70 something or 57. I'll try 57 first. Yeah, it's 57. So slide 56, 55. You can look at that link, or you can go to like 55, 56, 57. That's the Debye heat capacity equation. X4, E to the X, whatever. That's the same equation he gives. He gives it in kind of a different manipulated form here, but if you figure it out, it's the same thing. This equation 3 is the same. So it's got temperature cubed as a front. Then he's got that weighting, that W function, and then times this thing squared. So 1 over T squared, like in Einstein. So that's so 1 over T squared is the X to the 4. So because he's got another, see, he's got another, this is his thing, right? Where did I put his paper now? Did I erase it? I got rid of it. So, no, this is the B thing. Here, all right, so he's got T squared here, but he's got another T squared right here, 1 over T squared here. So that ends up being 1 over T to the 4. That's his X to the 4. And then the T by D to 3 is the standard, the low temperature for the Debye part. So when you put in the W, if you plug it in, you get the same equation as what's in the notes. The way he's framed it up is kind of interesting because this W is the Einstein equation for heat capacity. If you look at it, so he's inferring that the by heat capacity is just an integral of the Einstein guitar string model over the range of frequencies, which is kind of what it is. So it's like he's taken a bunch of Einsteins, weighted it with this term, and then integrated over the frequencies up to the Debye temperature. It's like the way he's framed it up, it's another way to look at where the origin of the Debye function is. Like if you wanted to derive the Debye function starting with the Einstein function, then you just have to say, oh, you just have to integrate it and figure out why that term is there. But basically, this is saying that the Debye function for heat capacity is the same as the Einstein, just integrated over a bunch of frequencies, not just one. So it's kind of nice how he did that. I haven't seen that in a book anywhere. It probably is in a book, but I haven't seen it. So anyway, people say that. They say that it's an integral of frequencies, but I haven't seen anybody show it like that, to exactly show it. So it's kind of nice what he did. Anyway, or basically I'm just saying go back to the notes and just go through it, and write it down. So how does it differ from the equation just before equation 2, which is the Einstein equation? So here's W is actually the Einstein equation for heat capacity. I mean, it differs because it's integrated, like it's integral of that thing, and he kind of shows that there. So anyway, and then how did he obtain the Debye temperature? So that's what I went through. So you have to kind of start here and go through what he does. He does it, or even before. So first he starts with the atoms. What it says so you can go to this vast plate. It says there's 3 steps. Set up the atoms, just put them in the crystal, and then do a fully quantum mechanical, like a density functional theory calculation for the electronic state of the whole thing. Then you have the whole thing set up, but it's not at an energy minimum. And then let it reach energy minimum by molecular dynamics or by minimize the forces, either one of those. And molecular dynamics seems to be the one that makes sense, especially in that's going to give you the vibrational spread of the thing. It's going to give you the density of states directly. So basically, and molecular dynamics is a way to go because it'll give you the answer that he wants, which is in the end, he doesn't care about the crystal structure. He wants the density of states function, this G of nu. So he can plug it into this equation with a sinc function, integrate it and get the energy, and then take energy minus the energy dt times t gives him u, and the derivative of u gives him the heat capacity, and then fit the heat capacity that you get with the Debye function and get the Debye temperature. It's not a long process. I don't know how many steps that was. I think it was like 9 steps. But that's what the answer to this thing is, kind of explain, like that's how he gets the Debye temperature. He doesn't fit the Debye equation to that thing that he got through that process. So I think maybe you got to like just read through this, try to make some sense of it, and just kind of say that, to answer that. Hopefully by the time you finish with that, you'll at least feel slightly comfortable with the whole concept, or you'll feel completely, absolutely confused. And just, you can fold this page and go on to the next thing. But basically the idea is like to give you something so you feel like if someone says that, oh, they got the Debye temperature, they're doing something with whatever, and you can kind of have a safe space where you can sit there and then reach off into the other things that are really complicated from it. Say like, at least I know that one thing. Or if someone gives a talk on it, it would be like a physics talk, which you may never hear, but basically if they do, you can ask them a question that makes some sense based on this. And then they'd have to be able to answer that. If they can't, then they don't know what they're talking about. So it's like a good to have a tool where you can ask a probing question, even if you barely understand what's going on. So anyway, it's a technique. So that's the idea. Like you won't become an expert in this. And if you see it, so you'll see it now, and then maybe you'll see it in like 10 years or something, you're doing something else. You get a job at like a microelectronics company, and you'll be like this will be really important to them. So, and then then you see, maybe you go like, oh yeah, I kind of remember that. At least you remember there's three things. It's like Dulong, Petit, Einstein, and Debye. But there's some difference between them, that you can kind of get a feel for where things are going. So I don't expect you to become an expert at it, but just to be able to defend yourself if someone asks you a question, or if you can put someone on the spot by asking a question about it. So that's about it for this thing. It's not easy, but it's all right. What else? I got a couple minutes. I'd like to try to go through a little bit. Any questions on this thing, or that? Right. It's not a good sign, but what else do I have here? We got like 15 minutes, right? I'd like to try to get through the heat capacity because I got a ton of stuff to do in here. Actually, we're kind of done with the important part of it. The other parts are more like nuances, and in the book goes through a lot of nuances that are so if you end up working with a certain like magnetic materials or something, and then there's certain electronic materials, then you have to, there's some things that are like well known, I guess. So, but he brings up really odd cases, examples that I think come from whatever they do in Finland or wherever he's from. I think the authors are from Finland. But I think they're from Finland, and the last chapter on simulations is a guy from the UK. So, but Finland's a good place for physics, it turns out, like strangely enough. But anyway, so what's this stuff? This is just showing the high temperature limit. I already went through that for the Einstein, but there's something else here. Oh, yeah, there's something else here. At some point in this paper, he uses this equation for the energy. It's like you make, so the energy is this kind of this would be the sink function, sine h, right? So if you, at some point in the paper, he gives this function, and it kind of just comes out of the blue. He says that the energy is quadratic. For the Debye equation, the energy is quadratic in frequency, which means square of frequency, which is this equation, right? This is the Boltzmann distribution of energy times the energy gives you the energy of one frequency, and you integrate that to get the total energy. But they'll say like the energy is a quadratic of frequency. He says that in this paper. So anyway, I think that's partly why this is here to show you that you get the Dulong Petit result. So 3R at high, for the molar heat capacity is 3R at high temperature. But on the way to get that, you get the quadratic equation of energy and frequency, which he mentions in the paper. So where does that come from? So exponential of a small number, smaller than 1, is going to be an expansion, like a power series expansion, 1 plus x squared by 2 plus x squared by 3 factorial plus x squared by 4 factorial. So if this is a really small number, you just take the first two terms, 1 plus that thing. So if you plug that in for the exponential here, and then the -1 kills the 1, and this becomes h nu over h nu, kills off, and you just have kBt up here, which is there. So that just solves that. So that's just, if you plug that into there, you get this, which is the quadratic function in frequency, which I think he says that in this paper at some point. Let's see. Like if I Google quadratic in there, I think I would find it. Is this his paper? Yes. Let's see. That's what I want. Well, that's because it's cubic boron nitride. Square root. Somewhere in here he mentions that that it's quadratic in frequency. But I don't see it. Anyway, anyway, it is in there someplace, but so that comes from that thing. So a lot of times they're looking at, so you have the also you have the thing like, so the harmonic approximations, you have the frequency versus wave vector like that. And then if you're, so this is that high temperature. So basically you have the frequency is proportional to the wave vector also, and the energy is proportional to that thing squared. So they'll just toss that out, like they'll just say that that's the Debye. They'll just say like that's the Debye approach or whatever. And it's just because they're taking limits of the function is the simplest point of it. So anyway, so I mean, this is a place where you get Dulong Petit from it, but it ends up giving you expression for the energy. All right, so there's that business. What else? So this is it. So here's the density of states as a quadratic of frequency. That's because the energy is quadratic of frequency. It's the same thing. So if you integrate that, that's how you get this. If you integrate this equation, you get this behavior, the cubic dependence of the density of states and frequency, which is the thing about what they show. The Einstein would be like one value, and then the Debye is this thing. It's because they get that quadratic dependence from this thing. It's like that gives that. So that's where this plot comes from. That's what it is. Like this plot. So the Einstein density of states is just one value. So you just have one population at one frequency, and the Debye has this distribution of frequencies because of this, because of that. Because you can take the energy from this expression using the Bose-Einstein distribution and get that thing in the limit of high temperature. And then that gives you this distribution that cuts off when you reach the Brillouin zone, or in other words, when the frequency reaches the end of the Brillouin zone, you don't have any more vibrations because they all repeat after that, because you get into frequency, into wavelengths smaller than the atom spacing. So lambda is smaller than A, so you can't get any more vibrations from that. It just repeats. They repeat for a factor of n for the as you go to higher and higher wavelength or lower and lower frequency. So that's why you have a cutoff, and that's why it's like here's with the Einstein, and this is the Debye. So that's kind of where that comes from. I guess that's the point. You get this cubic or squared dependence on frequency of the density of states. Anyway, so capacity, we've already gone through those things. And the Einstein's like 0.8 times the Debye, like it's a lower number. And then, so these are kind of what are in that paper, like diamond and graphite, Debye temperatures. Actually, you can use those for that to answer that thing if you want. Like the numbers are there on slide 70 for it doesn't give the carbon. Then there's a table with the Debye temperature and this other thing, which is the electronic part of the heat capacity. So I went through that already. The stronger bonds, you get a higher Debye temperature. And then I went through this already, how you get the modulus. And then this is the equation. So slide 74 gives that R-naught equation, that thing, to get the modulus, which is the same as in the paper. It's the last equation in the paper. By temperatures, heat capacity, so you can get the modulus. Let's see, so you can get the modulus and calculate the Debye temperature from the modulus, like using that equation, or you can just get this from heat capacity from the Debye equation, and the numbers are the same. I think I already went through that. And then there's this business of how you get this if you don't know. So if you're at high temperature where these things differ, and you don't know the thermal expansion coefficient, so you need to use an empirical function. So you kind of have a constant, and the constant is called the Gruner constant for this thing. It's the Grun-Eisen, it's a green ice parameter. So it's like this gamma G. So there's gamma, which is the electronic contribution. There's gamma G, and there's another gamma that we had. They use the same symbol for three different things. But this is this is to get the, if you don't know, I guess the bulk compressibility or what's kappa? This is thermal expansions, as kappa is the bulk compressibility, I think. Isothermal bulk compressibility, right? So if you don't know that number, then you can use this Grun-Eisen equation to get that. And the Grun-Eisen numbers are tabulated. Like you can look those up for every material. So basically then you can get the temperature dependence of this thing. So at absolute zero, there's no difference. And as temperature rises, as it gets larger, it depends on this Grun-Eisen parameter that you can look up. And the thermal expansion and whatever the CV is, which you can get from the simulation, or whatever, from the Debye equation or whatever. So anyways, that thing. This is that business. And then how do you get specific heat from the density of states? That's this integral that is in the paper. It's the same integral. Like you integrate the density of states, and then there's this Bose-Einstein distribution function, and then you can get the heat capacity. So that's the equation. The bottom one is the equation that he uses in the paper. So you already kind of know that, I guess. Anyway, there's question in the homework about how you get the heat capacity from. So his simulation is going to give him the density of states, and then he's going to use the density of states to get the heat capacity. That's a routine in the paper. Then there's all this business. So there is a so there's spectroscopies. These are like the standard spectroscopies. You have IR spectroscopy, infrared absorption, and then Raman spectroscopy is this. So those are like chemistry people use a lot, and you can use it also for crystals. So Raman's like this. So I got 5 minutes, I think. So both of them are looking at bond vibrations, right? So you have the bond vibration is kind of like a bell. And you're putting in this field. So this is going to give you the optical vibrations, they're not going to give the mechanical vibrations, at least IR and Raman won't. So the IR, you just shoot a beam of light in, it's got like H nu energy, it's got a certain frequency, it'll either ring the bell or not, right? So when you think there's a quantized vibration for that bond, and the bond can go, if you have 3 bonds, it could go like that, or it could go like this, right? So there's like various vibrations, and they could go in and out of the board. So that could be like 6 vibrations for a 3 bond molecule. And so basically, depending on the number of atoms, you can have different numbers of vibrations that the thing could go through. All right, so they're discrete, they're quantized vibrations that show up as kind of a spike. Sometimes they're broader. So generally, so if you other kinds of spectroscopy, there'll be sharper transitions, but basically this is just looking at the absorption from what's going on. Raman's kind of a different game. So in Raman, you're going to come in with the light. So you're talking about an electric field, like plus minus coming in, and it's going to move the plus and the minus atoms differently. That's what gives rise to the vibration, and it'll absorb the energy at the frequency that takes it, right? So with Raman, it's different. You're going to come in with the same radiation, but they're not plus minus, like they conjugated. So the electrons are free, so they can go here or there. And then when it's plus, they go over here. When it's minus, they go over here. That's called polarization. Right? And this is polarity. That's IR is like polarity, polarization is Raman. So what happens with Raman is you come in with H nu energy, and then that vibration, that polarization of the bonds leads to a vibration, and that either adds or subtracts whatever the vibrational energy of it is. So you're going to have the main peak of the spectrum you had coming in, and there's going to be a Stokes one and an anti-Stokes one. The other way around. So the Stokes one you subtracted, so you came in with the light, that vibration sucked energy off, which is the normal state of affairs, and shifted it to a lower energy. This would be frequency.
And the anti-Stokes, which goes the other way, it's already vibrating, it contributes to the wavelength of it. So if you do a spectrograph of the intensity, you'll see that your peak, when you shot it in, it had a single wavelength, so you have a laser, so you need a laser to do this. And you'll have two side peaks, the Stokes and the anti-Stokes. And the energy of the vibration is the distance between those. That's the h nu of the vibration, whereas an IR, you have a spike, it's at a frequency, the energy is h nu, that frequency where it absorbed it. They're different. So basically, those are going to give different kind of optical vibrations for the system, right? And the third technique is at a lower frequency, so a lower energy, so lower temperature. Right? That's this Brilliant. So that's the same thing as Raman, except it's looking at acoustic vibrations. So they're much lower energy than optical vibrations. So basically, you get kind of the same spectrum as in a Raman. You have Stokes and anti-Stokes. And the difference between the main peak that came in, the laser wavelength, and the frequency that you get from the thing is the absorption. So that's the spectrum, is the difference between those two. So this is just for one vibration. In a real system, it's going to have a lot of vibrations. This will be a spectrum. It'll be like a bunch of peaks. It won't be just one, right? So this is for something very simple. It's only got one vibration in it. So if you end up plotting like against frequency, so the Brilliant is way down low in energies, it's like acoustic vibrations, and optical are the high energy ones, like we saw with the graphite and the diamond. It's the high energy ones, so these optical vibrations, right? And the acoustic are low ones. So anyway, the Brilliant machine, there is a Brilliant, so it's kind of rare to find a Brilliant scattering machine, and there's one downstairs in Rhodes. So we could go look at it sometime. I don't know when you guys have time or if you want to do it. But basically, there's an instrument. John Nichols from Chemical Engineering has an instrument set up down there. It's kind of interesting to see, but it's basically this machine, this Brilliant scattering machine. I mean, there's other ways to get, so people do neutron scattering to get these kind of energy levels of vibrations to look at different phenomena that are going on. So Brilliant, this energy of acoustic vibrations couples up with like what they do at Oak Ridge in NIST for neutron, quasi-elastic neutron scattering to see the spectrum of energy absorptions for different vibrations and systems. Those people that just do this all the time, they don't make a lot of money. Basically they do it for some reason, they enjoy doing it, I guess. But anyway, people do this, and John Nichols is one of them. So anyway, if anybody wants to go see it, let me know and I'll schedule a time. We can go down and look at it. And he's got also a confocal microscope there that he uses with this setup, so you can kind of see what that is too, I guess. But anyway, so just email me if anyone wants to do it. I think that's probably the best way. And then if you email me, if it can only be one, it can be one person if it's no one else wants to do it, or it could be half a person. It doesn't have to be a whole person. But it'll be fun to do, I think. But he's got an X-ray scattering thing in there too now. So it would be good to kind of see it, especially if you're doing the characterization class. But so like that, seeing that machine should help if he talks about Raman scattering and the characterization, for instance. He won't talk about Brilliant because that's kind of for crystals. It's not exactly, they use it for organic, but it's not a standard technique like Raman. It's pretty standard, especially for like carbon buckyballs and nanotubes and things. Because there's a Raman absorption, because it doesn't have any polar groups in it. So it's got all Raman spectrum. Like all the carbon materials are just Raman spectra because there's no polar groups. So you don't get IR patterns from them. Normally any material look IR, it's simple. You stick it in and get the pattern. Right? But Raman's a little bit more difficult, I guess, in a sense, the interpretation might be a little. Right, that's about it. So up to slide 82. Out of like some bunch of slides. So I probably got like another half lecture on heat capacity. Then I want to go to whatever the next thing is. I don't even remember what it is, but something else so that we can kind of try to finish a sizable chunk of what we're supposed to cover. So what I kind of designed it to cover, but anyway, that's about it.